So now we can get started. So here we have Isabel Ojalvo with us today. She's an assistant professor of physics at Princeton. She earned her PhD from the University of Madison, Wisconsin in 2014. Before receiving her doctorate, she worked at the Boeing Space and Intelligence Systems in El Segundo, California, and was a Dickey Fellow in 2016. Her work focuses primarily on studying physics that decays into tau leptons using the data collected by the CMS experiment. She also spent many years working on the level 1 trigger system at CMS and working on the commissioning and installing of hardware and developing new high-speed algorithms. So with that, please join me in welcoming Isabel.
So much. It's lovely to be here. This is well, okay, inside it's a very lovely view, and I'm excited to come back in a couple of years when you have been able to expand your laboratories and research activities. So today I'll be talking about triggering on anomalies at the LHC. I will say I have a wide variety of interests right now. I'm also working on Muon collider, our detector R&D, and actually, we recently got a grant from the Simon Foundation to start maybe doing some accelerator work as well. Myself and a couple of other, Carrie DiPetrello and Tilbur Holmes. Today, I'm focusing on triggering on anomalies at the LHC. It's been kind of the bulk of my work. I started at Princeton as a faculty member in 2019. It's now 2025. This has taken quite a long time to actually get online for the CMS, for run 3. I forgot I can only use this for pointing. Good. Okay. So, just to give you guys a little bit of, can I move this? Let me turn this. Okay, good. That's fine. And that is okay too. Okay, so just to set the stage a little bit, I'll be talking about the level 1 trigger system. I'll define the level 1 trigger system in a couple of slides, but I just wanted to give you guys an idea. So this is, this is what the events at the CMS detector at the LHC looked like back around 2011. We had something like an average of 25 proton-proton interactions per collision. Now, we call this the legacy system for the level 1 trigger, also for the detector. We installed the phase 1 upgrade. I was quite involved in that in 2014, 2015. I'll discuss that in a couple of slides, but basically we took apart the entire trigger system and we installed these field programmable gate arrays. And so that gave us a lot of flexibility to think about how we want to do things for the run 3 trigger, which is now up to about 60 pileup. Something a little bit more similar to this with a lot more simultaneous interactions. So most of the work I'm describing today has taken place, is already online, in fact, in the last year or so. But I will also be referencing the HLHC, a lot of the R&D and the techniques that we used and developed for this anomaly detection algorithm. Were initially envisioned for the HLHC, but we are using it in run 3. So I just wanted to emphasize that what I'm talking about is for the current CMS data taking. Okay. And if I have a second, maybe I'll talk about the Muon shot at the end. Feel free to stop me and ask questions. People have various amounts of background with all of this. There we go. Okay. So feel free to discuss. Okay, so just to give you a broad picture overview, as you guys know, particle physics aims to describe the interactions of particles, so the fundamental particles, using quantum field theory. And this is basically combining, field theory with relativity to construct physical models. One might say that it started with Newton and this idea of action at a distance, so apple falling in a gravitational field. But that was a little bit, not quite there yet. Really, we could say that quantum field theory got started in about 1864 with the completion of Maxwell's equations. And so basically Maxwell used gave us a classical working of electromagnetic theory, which uses electric fields and magnetic fields to understand the motion of charged particles in fields. It just so happens that E fields and B fields propagate at the speed of light. And so this was kind of our first idea of using fields to discuss the propagation of various interactions. Right, so so far, quantum field theory and particle physics has been super, super successful. We've been able to use it to measure with a lot of precision, like the interaction between electrons and positrons, and the creation of dimuons. We've been able to understand very well the distribution of creation of Z bosons in the detectors at CMS, and think very carefully about how they're the particles that are coming out are distributed within the detector. And so, how are we able to do this? So in 1919, Rutherford realized that he could split nitrogen atoms by bombarding them with radioactive sources. Then in 1932, Krakoff-Walton used 400 kilovolt potential to accelerate protons and split them with lithium. This brought this up to 1929, where Ernest Lawrence invented the cyclotron, which was able to accelerate protons to 1.25 MeV in only a 4-inch diameter. And all of these inventions of mechanisms to accelerate particles led to the discovery of the standard model of particle physics, and a very good working understanding of how particles are interacting. So this is what our fundamental particles look like so far. You can see I like to put the years of discovery below. Most of them, nearly all of them, were discovered at various colliders. And this culminated in the discovery of the Higgs boson in 2012. And so we have a very complete and well-working model of standard model of particle physics, which we are able to make a lot of measurements to very, very, very high precisions. But of course, we have a number of open questions. And so this is actually one that I quite liked. I was at Aspen recently, and we had a public lecture. And the lecturer said, okay, so you look at this and, we have this structure here. We have the top quark, we have the bottom quark, we have the up quark, we have the neutrinos that are very many orders of magnitude less massive than the quarks and the heavy leptons and the charged leptons. And so trying to understand the fact that there is a structure at all, we have it's being split up into multiple generations. We have many orders of magnitude difference in mass between the neutrinos and the quarks and the charged leptons is really actually quite confusing for us. And so one would ask, okay, what is the underlying structure? And actually, it was kind of funny because somebody from the audience is like, what if that's it? Why does there have to be an underlying structure? And so my response was, at one point, Mendeleev was looking at the periodic table and organizing everything into the metals, the metalloids, non-metals, noble gases, etc. And eventually came to understand that this was due to an underlying structure, a nuclear interaction. And so the variations in the nuclear binding energies influence where the atoms show up within this table. And then we have electromagnetic theory, which also defines how electrons are able to transverse various orbitals and bind chemicals together. And so, yeah, I guess naturally, as somebody who really enjoyed actually studying the periodic table when I was young, I feel that there is, it would be very unsatisfactory to us as on a larger scale if we can try to understand a little bit more of what is causing, the differences in these generations and the differences in these masses. And we'd like to understand if there's some sort of deeper meaning to all of this, similar to what we were able to do with the periodic table. Another open question, of course, is dark matter. And this one's a very strong open question because, something like more than 95% of the universe is made up of dark matter and dark energy. So is there some sort of connection between the complex structure of the visible universe and the invisible universe, and we'd like to understand a little bit more, is dark matter something that we could possibly create in a particle collider? Does it act like a particle at all? Is there a large amount of structure to it, an underlying structure similar to what we see in the standard model? Yeah, these are all things that you could think, okay, I can use the standard model as a guide to try to search for beyond standard model physics. And so the best laboratory, or one of the best laboratories to search for these, to search for the creation of beyond the standard model particles, of course, is the Large Hadron Collider at CERN. So this is the highest energy particle collider that has ever been built. And yeah, it's going to be in operation until the 2040s. So we should do our best really to try to make use of it as much as possible, and search for any beyond standard model physics that we possibly can. And so with particle physics, there is a heavy ion program here. I won't talk about that in great detail. I do welcome my heavy ion colleagues as well. But my focus primarily is protons. Protons, of course, are like these bags of quarks and gluons with some probabilistic distribution of energy. So you have you have these very high energy protons that are interacting. You have a mix of initial states. This can produce a wide variety of phenomena. And so this actually makes a very, very nice discovery machine. And so while we have this really nice mix of initial states, what happens most of the time, of course, is that we have interactions between quarks and gluons. We have interactions with quarks and gluons. This is mostly reacting with via quantum chromodynamics. And so what happens, as you can see over here, we have the total cross-section that is many, many orders of magnitude. So something like 10 to the 8th nanobarns over here. If we want to search for electroweak physics or Higgs physics, this is like 10 orders of magnitude more rare than, for instance, just normal quark gluon interaction, like inelastic scattering or elastic scattering. So that means that the interesting physics that we want to produce is actually really, really quite rare. Okay, so we have a huge amount of particle interactions. We have lots of stuff coming out, but the physics that we're actually interested in is happening only very, very rarely. And so at the CMS experiment and also at the Atlas experiment, we generate huge amounts of data. So if our particles the interactions we want to produce are very rare, then we want to produce a huge number of those interactions so that every once in a while, we're going to be able to produce and pick up the things that we're actually interested in studying. And so I have a lot of people from the CMS experiment making fun of me because I know this is not the CMS experiment, this is the Atlas experiment. Data generation CMS, no, this is Atlas, but it's really a nice video and you guys have an excellent outreach team. But this, I think, gives you a really good idea of what it looks like to have these bunches of protons colliding, interacting within a general purpose detector. So here you can see that the bunches collide every 25 nanoseconds. And this is 40 megahertz crossing rate. Each event produces approximately 5 megabytes of data in the entire detector. And so just to give you an idea of how massive of an amount of data this is, I did some calculations. And so if you multiply 5 megabytes by 40 megahertz by, let's say, maybe 90 days of uptime per year during the run, this is hundreds of terabytes per second, or 1.6 zettabytes per year, which is 10 to the 21. And since it's hard for us to really think about orders of magnitude like that, I Googled it a bit, and 10 to the 21 is approximately the number of grains of sand on Earth. So you can kind of get an idea of like what sort of data filtering that we really want to do. And it's, just huge amounts of data that we have to be able to process very, very quickly. So what we do is we have multiple layers of selection at the CMS and Atlas experiments. So at CMS, we call this a level 1 trigger. I'll go into this in a little bit more detail, but just to give you a brief overview. We have custom built hardware. So this is able to read every single event at the 25 nanosecond rate. It takes in the data across these fiber optic links. We use these field programmable gate arrays to process the data. And so just to give you a couple orders of magnitude again, yes, so fast algorithms on custom FPGA boards. So I'll be talking in particular about the calorimeter systems. And so the calorimeter trigger system sees approximately 4 kilobytes per event. Okay, that sounds like not so much. But essentially this means that this is approximately 200 gigabytes per second. Or essentially our calorimeter trigger has to analyze approximately 200 high definition movies every single second and say, okay, pick out every single screen or scene where somebody's wearing a red, sweater. So you're really trying to process a huge amount of data, do image recognition, and process this super fast and with a super high fidelity, right? You don't want to be throwing out this new physics or these Higgs events. This would not be an ideal situation. And so just to give you an idea, only about 0.25% of the events are then sent on to the high level trigger for further analysis. So the level 1 trigger has to do a down select of 99.75% of the events. Those are going to be thrown away and lost forever. And the rest of the 0.25% are allowed to be processed for offline analysis. Okay, and so how have we been doing? Overall, the trigger performance at CMS has been doing fairly well. We were able to discover the Higgs boson in 2012. You can see on the right, I'll just show you a large variety of final states which we're trying to identify in real time. We have been able to, really use a large variety of final states like the diphoton. You can see Higgs gamma gamma on the left. We've been able to observe the Higgs decaying to taus in 2017 using the phase 1 trigger upgrade. Again, so we have a hadronic tau, a jet, tau decaying to muon, and some missing ET. And we've been able to perform many DSM searches. So for instance, here we have a Higgs doublet model plus scalar singlet. But so far we actually haven't seen any new physics. So where is the new physics? So this is something that has been plaguing, I guess, a lot of us, and especially on CMS and Atlas when we're collecting data, and one thing we have to wonder is, okay, do we need more data? Perhaps we need just a higher number of collisions. We can go to the HLHC. Perhaps we need a linear collider or a future collider that could go to a higher center of mass energy. It's possible that we aren't able to create new physics at the LHC. Maybe we need a muon collider or FCC-HH. But of course, the thing that is the scariest when you're operating a multi-billion-dollar machine is, are we missing the new physics at the LHC? Are we, someday am I going to be, sitting in a retirement home someday somewhere and realizing that, oh, we should have looked in X corner and we would have been able to see everything. And there are a few times in history where an experiment could have picked up the new physics if they had looked in the right places. And so, until we have the opportunity to operate the HLHC and gather a lot more data, or perhaps go to a muon collider with a higher center of mass energy, we try to think, okay, how can we trigger on new physics at the HLHC or the LHC? So we had this workshop in 2018. And basically, so we call it triggering on new physics at the HLHC. I will say most of these ideas have been now implemented actually in run 3. We invited a bunch of theorists basically to break the trigger system for us and just tell us, okay, what is it possible that we could be missing right now? And so they gave us some really excellent models. So we discussed things like long-lived particles. So here we have a Higgs decaying to two two long-lived scalars. And so we looked at ways to detect these in both the calorimeter system. This was using HCal timing. This is for scalars that have maybe a C tau of about 1 meter and will decay primarily in the calorimeters. We've also implemented Muon detector showers, which would have a C tau of approximately 1 to 10 meters. They were also started to propose things like emerging jets. So I like this in particular. So basically, emerging jet postulates that a QCD like non-abelian gauge symmetry exists, and essentially you will have a dark sector that has the same amount of, let's say, complexity as in the dark QCD as it does in standard model QCD. And so basically the idea is that the dark sector is able to interact with standard model quarks through a dark mediator, which is charged under both standard model and dark QCD. And so this could look like some emerging jet where you have, well, we call this an emerging jet, where you have some delayed signature either in the calorimeter system or just some amount of missing energy that's going to be scattered about the jet. So a darkened signature within the emerging jet. They also propose things like soft underlying energy patterns or SWEPs. So basically what happens here is that we have the signature is an isotropic spray of dark pseudoscalar mesons decaying into pairs of dark photons. And so the idea is that these dark photons undergo kinetic mixing to the standard model under hypercharge. And so this will basically create this very like spherical distribution of spray of particles within the detector. And you will see a bit of a different distribution compared to QCD because of like the symmetry around the detector. And so both of these were really challenging ideas that they gave us that that are now being much more considered in terms of analysis. And of course, this was in 2019. And so we had to kind of decide, okay, how do we want to expand our field of search as much as possible before the end of the run, which at the time was about 2024, 2025. And so the question, of course, is how can we search as much as possible for anything that we could possibly be missing? So this is when we took an opportunity to rethink how we trigger on rare physics. And so instead of going for supervised detection of particles, we tried to go more towards anomaly detection. Anomaly detection has been developed in the 1950s and 1960s. And basically what we do is we try to take a distribution of data and then look for outliers and try to cluster the outliers. And there are a variety of techniques of ways to do this, but I will say, I will shorten it a little bit just to discuss what we're working for or looking for. Both supervised and unsupervised, and this is great for searching for unknown signatures for news physics. And I will also actually, since I do have my Atlas friends here, the first anomaly detection search that I'm aware of was done offline by the Atlas collaboration. And so since that was published, we've been trying to catch up over at CMS. Right, and so of course, this idea of searching for unknown signatures for new physics is that our standard physics may evade the standard cut-based selections. So yeah, if our selected data is over here, we have some sort of trigger threshold. We say, okay, we want at least 50 GeV worth of energy. What happens if the new physics is below that threshold? So this is just a very simplified model. Particle physics signatures can also be very difficult to label. They could be a superposition of quantum states, making them, a superposition of quantum states so that you don't actually know, is this definitely, from this particle or that particle? And so anomaly detection is particularly useful there. And of course, with machine learning, image recognition can really exploit these topological features, which we'll be doing, which I'll show how we were able to do that as well. So the idea is to implement something that is as model agnostic as possible. And of course, I will motivate this all and say that once we identify a signal of interest, we have to be able to go back and actually trigger on it with some amount of, the cut-based or supervised trigger. We have to be able to go back and look at what we were able to detect and see why we were able to detect it. So just one more slide on anomaly detection applications. So I'll discuss this. We were actually able to get funding for this research through the Eric and Wendy Schmidt Foundation. But of course, anomaly detection applications are really super broad, from like cybersecurity, finance, healthcare, patient monitoring, et cetera, telecommunications. So it's been a very it's a useful field of study for all sorts of applications. Just to give you an idea, so we are using an autoencoder. I'll be discussing autoencoders today. So how to search for something when we don't know what we're looking for. So basically, we try to target events that are non-background like. So red flower versus white and yellow flowers. And so what we do is we have this ML architecture where we have input data, we encode it into some latent space, and then we try to decode it and deconstruct it into the full input phase space. The idea is to make it unsupervised, and so we don't try to label each of the encoders and the decoders. And of course, so these are neural networks that are trained on a large number of events, a large number of background events. So the idea is that if we have something that we've seen very many times, we'll have a similar input compared to the output, which will be a low anomaly score, or we'll have a different, if we have a different input to the output, this would be a higher anomaly score. So if we've seen this sort of event very often, low anomaly score, not so often, high anomaly score. Any questions at this point? Because next I'll talk about implementation in the CMS level 1 trigger system. I just wanted to do a bit of an overview, so setting the stage. Okay. And I'll also say that, as a trigger, a lot of this will be talking about in the next couple of slides, tools that go into all of these things. So putting this online for Run Free was quite the endeavor. We only had a short amount of runtime. We are going offline again in the middle of 2026 when we take everything out. We tried to install the upgrade for the phase 2 system for the HLHC. So I'll talk a little bit about the implementation into the CMS trigger system, but also discussing the ingredients that go in FPGAs. We use the Calorimeter trigger. We use high-level synthesis. This was also funded through the Eric and Wendy Schmidt Foundation, which then went on to fund the Next Generation Trigger project, which is now at CMS and Atlas. We also are working with the Dune collaboration to develop this autoencoders and anomaly detection systems for neutrino physics as well. So they're using some similar methodologies, and we're working with the group at Columbia for that. Okay, so where were we? Basically, at the end of run, when we installed the phase 1 trigger, this is a phase 1 trigger upgrade, or the phase 1 trigger, we use large reprogrammable gate arrays. So we have the calorimeters here. So electromagnetic calorimeter, hadronic calorimeter, forward hadronic calorimeter, the muon systems over here, which would reconstruct muon tracks and then go on to a global muon trigger. When we installed the phase 1 upgrade, we actually ended up having these very large FPGAs that in the end had some available space left to us. So we targeted the layer 1 calorimeter trigger system, mostly because we were aware of the fact that we actually had these large FPGAs available to us. They also have access to all of the calorimeter information from the electromagnetic calorimeter, hadronic calorimeter, also the HF. The trade-off, of course, is that we have to create a super fast algorithm. So right now, for the phase 1 implementation, the calorimeter trigger is simply taking the ecal and the hcal energy, summing them up into towers, into towers, and then passing this information onto the layer 2. So what we ended up with are links that are fully utilized. So we weren't actually able to do a lot of data sharing on the front on the front of the links, but FPGA logic, which is mostly empty, because as you can imagine, simply summing powers doesn't actually take a lot of doesn't take a lot of logic. And so overall, the idea was to target a run-free trigger system, so implementation in 2024 and 2025, and then use this information to gain experience for the high luminosity LHC. So still just to discuss a little bit about the tools. Actually I went a little bit quickly. I will show one more point from this slide is that this entire operation going from the data being collected at the calorimeters, at the Muon systems, all the way to when we have to decide whether or not an event is going to be selected for offline analysis has to happen within 120 bunch crossings, or about 3.5 microseconds. So this is very, very, very fast. If you put this in terms of clock cycles, we basically have about 6 clock cycles per bunch crossing. And for the layer one itself, we have approximately 200 nanoseconds that we would be able to do all of the analysis that we want to be able to do. But that's actually pretty good, because field programmable gate arrays are these excellent tools. They're reprogrammable. They are more energy efficient than CPUs and GPUs, and also more flexible and efficient design than an ASIC. So it's kind of like this trade-off. So whereas with CPUs and GPUs, a lot of the energy is actually used up waiting for processing logic or taking the data onto and off of the device. You can actually program every single little logic movement across an FPGA, and so super efficient, able to be very fast. But with an ASIC, of course, their design time, if we want to design an ASIC by hand, it takes a huge amount of time engineering an iterative process to actually get it right. So it's kind of a trade-off between these two things. The building blocks for this, of course, are DSPs. These are basically multiplier units that can perform arithmetic. We have lookup tables, which are indexed arrays, flip-flops and registers essentially, and block RAMs memory. And so each time we want to write something into an FPGA, we call it burning in, and these switching blocks are connected to connect various pieces of the logic. And so we just have this huge amount of resources that we're able to do, or that we're able to make use of in FPGAs if we do this all correctly. And in general, these are programmed with registered transfer logic, which is this very low level, a very low level language, which I'll talk about in a couple slides. So at first bat, you might think, okay, this actually could be quite complicated to try to implement machine learning algorithms using FPGAs. But at the core, machine learning algorithm does something like takes an input layer, perform some addition and some multiplication, have some activation function, and then you get an output layer with some value. Perhaps you want a vector, perhaps you want a single value. And in the end, this is actually quite well mapped to FPGAs. You can perform the multiplication and the addition using these arithmetic DSPs. Activation layers, which basically take all of these inputs and then transform it to, let's say, a high discriminator value or a low discriminator value, can be implemented using lookup tables, flip-flops, and VRAMs. And so the FPGAs that we have 1,000 DSPs, 204,000 lookup tables, and 2.5 million flip-flops, 27 megabytes of VRAM. So really a huge amount of data or a huge amount of resources that we're able to use. And we have this excellent new tool that we've just been really starting to grab a hold of at CMS called high-level synthesis. So this is Xilinx. A number of different industries have started to develop, or a number of different companies have started to develop various levels of high-level synthesis. And essentially, what it does is it takes something like a high level C function. Let's say we just have an adder here where we have C. We want to add 1 every time we access this unit. So an 8-bit counter, for instance. If we were to write this in C, this is only about 3 lines of code. If we were trying to write this in Verilog, this is something on the order of 10 lines of code. And so if you're able to, so high level synthesis essentially just takes our C and is able to encode it in RTL Verilog. I will note that it's been a very useful tool so far, but HLS is a disruptive technology. And so it's very important actually to know how FPGAs work. Otherwise you can fall into some really big issues trying to build something that's impossible. So calorimeter image convolutional anomaly detection algorithm. So I gave you all of the ingredients. Essentially what this algorithm does is it takes as input, it takes the whole calorimeter image here as input, encodes it into a vector representation, and then decodes it back into the output. And then our anomaly score is simply the input minus the output, the error between the input and the output as an average. So anomalies are defined as rare occurrences and should be poorly reconstructed.
So Isabel, question.
Mhm.
So in this context, is a 4-top event a standard model event that's very rare also in the category of anomaly?
Yes, exactly. Perfect. Yeah.
So you can use that to validate, and that's not a problem for you. That's a feature, not a bug? Or
That is a
it-
perfect feature, yeah, because of it, yeah, it has been actually helping us measure the efficiency of these algorithms. Yes, thank you so much. Yeah. And I'll also say that when I'm talking about background events, I use the term zero bias data set, and this is data that is being collected without any without any triggers requirements. So this is how we do a lot of our measurements. Are there any other questions while I've been waiting for it? Okay, yes, exactly. And exactly what Sarah said. If you remember the cross-section plot I showed previously, you know, the top quark production or lecture week, that's super rare. So is that actually something we'd expect to be able to detect with this algorithm? So yes, our input is a 2D tensor of calorimeter region energy data, and our encoder and decoder are convolutional neural networks. And we use unsupervised learning to train on zero bias data or this randomly selected background data. A few tricks of the trade. Quantization has been very important. So essentially we manipulate every single layer and the arithmetic we use at every single layer to optimize for how many bits each of the numbers, like each layer needs for multiplication, or what precision is needed at each point. This is a very useful way to reduce the amount of resources needed. Another thing that has been very useful is knowledge distillation. So we have the teacher model here, where we have the input, we have the encoder, vector, decoder, and output. And then we get the anomaly score. With the student model, we have taken this entire system, we calculate the anomaly score, and then we just calculate the anomaly score directly using a neural network rather than trying to complete the full chain of encoder and decoder. Because in the end, this is actually, the portion that we care about. There is some interesting area of research right now that tries to output extra information so you can go backwards and try to understand the selection process a little bit more, but I won't go into too much detail there. I will show a comparison between the teacher and the student model. The HLS4ML package has been super key to this implementation, and we've worked with this group to develop more packages, or to develop convolutional neural networks that are then been implemented in HLS4ML. So just to give you an idea, here we have background data set here above. Here we have a SUSY sample, basically heavy Higgs to 2Bs where the Higgs has a mass of 350 GeV. We have the original here, original input, with a reconstructed output, and then we have the mean square error. This is with the teacher algorithm. And you can see basically the anomaly score distribution over here. The dark blues are the zero bias background data, and then we have a very, a variety of signal samples on the right. So in yellow, we have soft underlying energy patterns. In green, we have long Higgs decaying to 2 long-lived particles. In pink, we have TT bar, and then we have the SUSY sample in dark red. So clear, a clear difference between signal and background. One thing I'll point out though is that these few guys over here actually considering how many orders of magnitude difference we have between zero bias and rare physics, those few guys actually do cause us quite a lot of headache. But you know, overall, it is expected that we'll be collecting some amount of background.
Isabel, can I ask another?
Yeah,
Sorry.
No, go for it.
It's like a literal map of your calorimeter.
Yeah.
You understand that? So one of the challenges I've seen with all of our attempts to use images in terms of doing physics is the representation of the different layers of the calorimeter and how they match with each other. So how do you handle that at level 1 for CMS?
So for instance, actually, well, one thing I think kind of maps to your question is that we've actually had to implement padding. So when you get to be wrapping around, you know, let's say your interesting signal like really falls here.
Yeah.
And so we do things like padding. So we'll put like a little bit of the roll over here and a little bit of the roll over there. So it's actually able to wrap around and get that full calorimeter image.
Okay, awesome. And you don't have to worry about different granularities in different layers.
Actually, we do have to worry about granularities in different layers, and you can actually see this in the efficiency later on. Not in these plots today, but it is something that is a bit of a headache actually. Is
It's
trying
a bit
to
of a
speed it
headache.
up. Yeah.
Okay,
So,
all right, yeah.
so I won't. Yeah. It's.
So you have 8 orders of magnitude between the headache events, as you said.
Yeah.
And the overall rate.
Mhm.
Isn't that about right for TT bar? I mean,
Yes.
So aren't they
Yeah.
really good headaches like TT bar?
Yeah. So yes, exactly. So they in general they are good headaches. But it does, but okay, you know, actually they're a pretty good headache. I'll show you the TT bar sample later on. But yeah, that is exactly right. And a lot of a lot of these zero bias events actually are probably TT bar. Yeah. Mm-hmm.
Can you elucidate a little bit more on
Yeah.
like strategies for like dealing with these like headache events?
I mean, well, actually, it's a good point. So I shouldn't call them headaches so much because, in fact, if, for instance, TT bar is quite rare, it's something that we really want to be able to see. We have decided that we don't want to. I mean, one thing that we had been considering is like, okay, we know that there's TT bar already. We're already collecting it. Do we want to train to select against it? And I think we don't want to do that next, but for now. But eventually, maybe it is something we have to do. Is say, okay, take the anomaly detection trigger only trigger, require this anomaly detection trigger if we don't trigger anything else, for instance. I think we don't want to do that yet, but it's something that we should be considering as we go to the HLHC. Does that kind of answer your question? Okay, thank you. Very good questions. Okay. I just wanted to flash a comparison with knowledge distillation of where we got with this. So we only tried it once because it was a huge headache to try to implement the teacher on an FPGA. 323,000 parameters for the teacher versus 3,000 parameters for the student. So it was just, for the current trigger implementation, there would be no way to put this on a single FPGA and make it run within the 200 nanoseconds that we need to be able to process the entire thing. The student, though, with going from 300,000 to 3,000 parameters, mostly preserves the performance. The inference latency here is 100 nanoseconds. Once you start offboarding the data, it gets to about 200 nanoseconds. But we were able to make the computationally fit into a single board. And just to give you an idea of the performance, here we have the teacher anomaly score on the left and the student anomaly score on the right. One thing that is quite fascinating and true across very many areas of machine learning, so this is a well-known feature at this point, that the student actually performs better than the teacher. So essentially the idea is that the student is possibly learning these soft labels, whereas the teacher is just doing very generic, unsupervised, encoding and decoding, the student is actually being able to learn the various features that the teacher, that the teacher is able to identify in the encoding and decoding. And so, we have 5 thresholds which we have implemented. The loosest is over here, the tightest is over here. Although actually I think we're now, that's about 135. We're at 135 for our offline anomaly or for our online anomaly score. We have found that we are somewhat sensitive to pileup. I'll just show what it looks like with a rock as well. So here on the y-axis, we have efficiency. On the x-axis, we have rate. And so our efficiency is pretty good. Stronger than so we, just to give a comparison, these dotted lines are what we'd say is like, let's just try to take the calorimeter and add it up and create an HT. So this is what the efficiency and the rate we're looking like for. For instance, yellow is soft underlying energy patterns is SUIPs, and here in green we have Higgs to two scalars that were long-lived. And you can see that we've gone from a very low efficiency to 20 or 30% efficiency at a trigger rate, which is approximately what we're getting, which is about 200 hertz. Or yes, so about 200. About 2 kilohertz for the loosest and about 200 hertz for the tightest. So, okay. Another thing I'll point out is that our area under the curves are all quite high, but considering that we need so many orders of magnitude reduction in rate, it's a little bit deceiving. We do have to cut quite stringently, and these area under the curves will still result in a reduction of efficiency. Another interesting point is that we have about a 50% overlap with existing triggers, which is, again, kind of good. We're picking up things that we want to see. And so, so this is our current performance. We went online for about a week at the end of 2020. What year are we? It's 2020, 2024. I'll be honest, I'm really just waiting for 2027 and the midterms. So just trying to bring forward. So I'm trying to forget that's 2020. So I'm like praying for 2027. Anyways, sorry. So I have to remember what year it is. Anyway, so we're going to be online again for 2025 and then 2026. I can talk a little bit about the firmware and hardware. Are there any questions at this point? Since I know that this is the data analysis is usually the most important point. Although being kind of somebody who likes the hardware stuff, I can't help but put in a lot of firmware and everything. So yeah. Mm-hmm.
Yeah. So in slide 32, is there a reason why the zero bias distributions are more to the right for the student?
As opposed to
like the tails seem to be longer.
Well, an interesting point is that so you do have the tail seems to be longer. We have actually so there is a rather broad uncertainty. So basically the error between the student and the teacher, how well the student is instructing the teacher is somewhat broad. I would have to think, I haven't been asked that question before, so I'd have to think about why if the tail is broader with the student versus the teacher. It could also be a bit of a sculpting effect between the two. I guess you can see it maybe a little bit better. Well, can you see it a little bit better with this plot? I mean, what this plot kind of tells us actually is that the student is far outperforming the teacher at these super low rates, if that gives you any idea. Basically, what seems to be happening is a student introduces more stringent cuts than the teacher would have. I don't know if I'll think if I can come up with a better answer. Mm-hmm.
So I have a similar question. So if I understand correctly, the student is trying to predict the score, which is like the loss of the teacher, right? Mm-hmm. So I don't really get why the student can be better than the teacher, because everything it can learn is the teacher's prediction, right? It can only.
Well,
utilize
this is an excellent question, and thank you for asking it. So one thing that we have had to do is kind of weight the student with higher anomalous score events, because otherwise we don't even have enough events to train for the region of phase space that we're interested in. So that can also be part of the effect there, is the fact that we have to weight the student with the high anomaly score events. So that could also be another reason why. It's something that it's been a little bit annoying having to fine tune that, to be honest. And it's definitely not a perfect science at this point, but it's because it's something that we could definitely study for a lot longer. Does that help?
Yeah, it helps.
Okay, yes, thanks. But there's a lot of things that are going into it. And really from machine learning as a broader point of view, there are many papers on what students outperforming teachers and soft label learning, et cetera. So it's, so it's beyond just what I have time to talk about or show here. So yeah, okay, great, thanks. Is there another question? We're good, okay. Okay, I'll just flash through some firmware and hardware implementation just because I'm a bit of a nerd that way. So basically a few things like, okay, so at CMS for the long term, for the level 1 trigger, we're going to this whole level of abstraction where we do all of the core firmware in VHDL, which is, you have a large amount of precision. You can do floor planning, you can really, you can manipulate buffer size, et cetera, and control everything to a high level of degree, which is great when you want to onboard and offboard data, and you need, and you need this level of like fine-grained manipulation of the firmware. We are doing nearly all the algorithms for phase 2 in high-level synthesis, and so far, actually, at CMS, we have built, basically our entire level 1 trigger system in high-level synthesis, the C++ implementation. And so this is actually the first time where we've done this online at CMS, making all of the algorithms. Basically, the core firmware handles all ancillary functions for the FPGA and brings the data to our core algorithm, where we then use high-level synthesis and C++ tools to synthesize. Definitely not a perfect way to do this. I just wanted to show you as well. This is the layer 1 trigger. Data comes into each of these crates. We then concentrate them across the backplanes, bring them to this one card here with where our CICADA algorithm runs. Essentially, we have one card per crate. It receives all the data from, we have one slice. We have ADA split up. So basically it has everything in ADA, but one slice of phi, everything in ADA, one slice of phi, everything in ADA, and one slice of phi. And then we concentrate this all through the backplanes, through the front panels, sending it all to a single card within one of the crates. Okay, so everything is brought in, concentrated into one crate. It also means that we have 2 more cards. So we're using this card for our CICADA algorithm. This one is completely, this is mostly empty, and that one's mostly empty. So we could do more algorithms if we have any people who are quite ambitious, but it has been quite a lot of work to try to implement this online. Just wanted to show you an eye scan of the backplane links here. Very nice
Could you go?
diagrams.
Could you go 3 times faster by using all 3 and then get more complex?
Yes, so this is something that I'm having students, so it's not something that I think we would have been able to, to implement for run 3, but distributing the inference across multiple layers could be super useful for this. So we've thought, okay, what if you can, evaluate here and here and here and just bring everything together at the end. We would need to, I think we need to reevaluate how we would do that because we lose some amount of data as we are going through the multiple layers of encoding and decoding. So perhaps we want to send a different amount of data. So the efficiency isn't quite as good as we want to try these distributed algorithms, but it's definitely something that I don't know, was that what you're trying to get at there, maybe, or?
I thought you were using one of these 3 and the other were just sitting there.
Yes, yeah.
And you could parallel process,
Yeah, well,
therefore taking longer.
in the end, we need to eventually calculate one score,
Per event.
per event, yeah.
Oh, so you're saying there's a
Yeah.
limiting single processor beyond this? I see.
Yeah, so, well, so, and so what actually, yeah, I mean, I guess if we were able to actually calculate, so this, for instance, this crate has one section, one, region of phi, this is a different region of phi, and this is a different region of phi. So if we could just calculate the scores here, here, and here, and then bring it back together, then that could be faster. That would actually probably increase, but it's something that, yeah, my group is, currently studying. We don't have a good implementation yet, but we'd like to study more for phase 2, yeah. But yes, it's true that would reduce basically speed things up, yeah, by not having to send all the data. Yeah, and just to say that once we concentrated all the data, done the processing, we have a single fiber connected to the global trigger. Yeah. So, okay, just to give you an idea, we had with the offline software integrated for first efficiency studies in 2023. First production was online in May of 2024. Well, online it was implemented. We realized we were at 18 VX for bunch crossing for our total latency. And we need to reduce that down to 12, which was really stressful actually. But in fact, HLS has a pragma that really allows you to force the latency as much as it can. And so we were able to reduce down to the 12 bunch crossings. We actually observed some link instability in June 2024, which are still a little bit. It's something that is still a little bit to be understood. But luckily, we had already been developing automatic resyncs. So basically, with a checksum, you detect whether or not you've gone out of synchronization. You see errors on it, and then it will initiate a resync procedure on the receiving end of the link. And we're able to implement that. So that was an automatic link alignment developed for phase 2 and implemented in run 3. So really, we've had an opportunity to test a lot of phase 2 things online. And yeah, so we were able to get first physics in October of 2024. You can see what our rates look like in the run. Yeah, and so it's been an interesting journey. And I'll show you actually, sorry, one more thing for first physics because we're talking about top quark. So this is just showing randomly selected zeroed bias data. This is with no CICADA score, but with the selection of, there must be at least 3 jets in an event. One is BTAG, and then 2 are there. Then we have 2 more jets as well. And we're taking invariant mass of the 3. So we call this our reconstructed top quark mass. And if you apply a CICADA score of greater than 115, you see a nice peak at 174 GeV. So basically we're using this to search for top to begin with. And then once we learn all of our lessons from trying to get a top quark, a top efficiency measurement, D-bar efficiency measurement, then we will go and try to search for new physics. Okay, so I will leave it there with our event display. This is one event that was collected with CICADA, which wasn't collected by any other trigger back in 2024. So, okay, thank you so much for your.
Great, so maybe if anyone has some questions, open it up.
So I'm just curious, does anyone ever check the events which are captured by the anomaly detection trigger, but not by any other trigger? You mentioned it's like 50%, but do they look like, yeah, how different are they?
Yeah, so they look very messy, to be honest, these very multi-jet events. So it's going to be interesting analyzing this. On the one hand, yeah, this is kind of, so whether or not this is just very, very complex QCD or this is something beyond the standard model, I guess we'll have to perform some searches offline and decide. But in general, you can think about how, yeah, an autoencoder works. You try to look for error between the encoded and the decoded. So you can think that a busier event would have maybe a higher probability of having a high loss. So it's a little bit, you know, yeah, these high multiplicity events are quite interesting. I think it could also be an interesting area of study, both from the QCD point of view, because this is a really complex interaction, but also new searches, if you're looking for like soft interline energy patterns, have very many deposits in the calorimeter systems. Yeah, the overall goal was to try to pick up things that you might not get from a normal trigger system, and yeah, soft interline energy patterns where you have this large distribution of busy calorimeter hits, or a busy calorimeter is a place where you might get that. So yeah. So yeah.
How well you can simulate the behavior at level 1 that you see. Can you actually do a top cross-section measurement using those events that you found?
We're trying, actually.
You are,
Yeah,
okay.
we're really trying.
That's
Yeah,
great.
So
Okay.
what we definitely have to do some efficiency. The efficiency is a bit lower in the Monte Carlo. Yeah, I basically went through the whole process of trying to estimate, how many TT bar events we should have. We're about, I think, on the order of 60% of what we would have expected, but okay, not all of the, so we're really like at the beginning, but yeah, exactly. So I think it's cool.
Yep. And a measure of how much zero bias data you need to be collecting to support this as well.
Well, we've been pretty good. The CMS does collect many terabytes of zero bias data. The problem is keeping access to it, because usually they put it on tape, and so it's been trying to get enough background events has been interesting. One thing, I don't know, it's possible we'll be kicking ourselves later for not collecting more background events like pre-scale lower scores, but I guess we will find out in the future. You'd think that the search, hopefully our loosest trigger is going to be our background, and then a tighter trigger is going to be our signal. But this is all we're trying to develop the analysis strategy. So yeah.
And you're going to have to adjust to changing LHT conditions.
Oh my God.
Right? Yeah.
That's been
super interesting.
That's been the bane of my existence. Yeah. No, it's okay. It's that has been the changing conditions has been a huge headache already, to be honest. So yeah. But you could do things like dividing by the overall. One thing that we looked at that was really cool and helped with stability was this dividing by the sum ET. And that already it is robust to like detector conditions, so calibrations. It's robust to pile up. You do lose a little bit of performance, but it does, it's stable at least, so that's nicer. But it's been a trade-off. So yeah. Do you have a question too? Yeah.
Yeah. I guess this is still pretty new, but have there been any other analyses based on this trigger apart from just the check on TT bar?
Oh yeah, so we're currently working on the emerging jets. This has a huge sensitivity to emerging jets, but also then I think soft interline energy patterns. But I think the real true goal is to repeat basically what Atlas did and try to do a bump hunt with data collected with this trigger, because like that's doing a model independent anomaly detection analysis should be the goal here. But I think, I guess I feel that it is good. Well, you can see this across very many detector or very many papers, like, so Higgs to BB bar, they wanted to see the peak in Z to BB bar before they felt very confident to unblind with Higgs to BB bar. So yeah. So any other questions? Yeah.
So for the emerging jets, is that cut by just the CICADA algorithm, or is that part of the thing that you've been triggering on before part of the 50%?
Yeah, so what we were using to trigger on those previously, I think they were actually in using the single muon trigger if you had an emerging jet produced in association with, I think it was in association with or Z or W boson, but also you can use things like HT initial or you can have initial or final state radiation. And so there are other trigger options. Oh, and then one more is of course the HCal timing trigger. So looking just for slight delays, because you can imagine if you are going into this dark sector and then coming back, perhaps you're going to a more mass particle, it's slowing things down, so perhaps you're going to have a little bit of a delay in the hadronic caliber. So there is some, depending on the model, there's some sensitivity there as well. So yeah, and then the CMS detector, people at the CMS detector like to call it trigger soup sometimes. It's like if you really just like, okay, I will try these large different distributions. So we're trying to, there's a large number of trigger strategies for these dark sector analyses. But yeah, the emerging jets has been interesting. But right, so far it looks like this CICADA should add a lot of sensitivity to a number of emerging jet models, especially ones that where it's really calorimeter focused and not so much tracker and not so much Muon system. So I don't know if that answered your question.
Yeah.
Happy to talk more. Yeah. All right. Cool. Thanks. Yeah.
Thanks a lot, Isabel,
Yeah.
nice to see you.
Yeah.
I was curious, given also your involvement in future colliders, is there anything going on also that front?
For anomaly detection, well, actually, so this is completely off topic, but I will say it because I thought it was super interesting. I'm really interested in muon colliders, but muon colliders are going to have like a collision every, I think it's even, I should look it up again, at 1 hertz. It's really a low event rate, like a super, super low event rate. Because it's high energy muons, that's fine. Actually, you get enough, you do get enough events, but it's a triggerless readout. Until a theorist was telling me about if you want to do multi-TeV neutrino detection, so then you'll have like this muon decaying down the beam pipe and producing a multi-TeV neutrino that is then super boosted, and so will then pass through your detector. And that, so basically you'll have that every other event, you can have a multi-TeV neutrino passing through your detector, which I thought was super cool. And then we might need a trigger again. So that would be, it's like, okay, good. Back in business, exactly. It's like, thank you. But yeah, I think, regardless, I think, doing onboard machine learning is going to be extremely important for a muon collider, because you need to try to do on-detector clustering, for instance, and only selecting a small amount of especially for beam-induced background. And then FCCHH is like, yeah, like that'll be a completely different ballgame. So yeah, thanks. Okay.
Great. If there are no more questions, we can
Thank you so much, everybody.